All right. We are live. Let's go to work, gentlemen. We've got a whole slew of content here that we need to get through, and we're going to be talking registers. And boy, do we do some lab testing. So I'm going to throw this on the screen real quick. We've got a whole presentation to get through. You ready, Steve? Ed?
I'm ready.
So just to introduce ourselves to anybody who's watching who maybe is in here and doesn't know who we are. I'm Chris Hughes. I do business development for the Energy Conservatory. Steve in the middle there.
I'm Steve. I'm the president of the Energy Conservatory.
And I'm Ed Jonawak. Yes, that's how you pronounce it, Jonawak. And I work for ACCA.
All right. So let's just to jump in this, let's talk a little bit about what we did. Who wants to kick it off? Me or Ed or Steve? Who wants to take a run through?
Have Ed go for it.
Okay. I never have a problem talking. So I think everybody knows that. We have questions nonstop about stuff. And there are very few things that bring me more joy than getting the answers to my questions. And I am fortunate, we are fortunate as a group that we get to spend a couple of days once or twice a year to go measure stuff. And this is one of those topics that is near and dear to my heart, simply for the fact that I'm a big advocate of proper design, and proper design is a product of figuring out how many BTUs we need to go in a room. Then we figure out how many CFM need to go into a room. And we can use some design guidance to do the things to find out how much air we have to blow into a room. And one of the most overlooked things when it comes to designing a system is what's on your screen right now. Grills and registers are, for the most part, ignored. To the point, and I'm not exaggerating when I say this, when somebody says something to me about register selection, and they are actually talking about looking up the engineering data for a grill or a register, I am genuinely surprised, because I don't think I'm exaggerating when I say that the vast majority of systems that get designed and installed in the lower 48, this part is ignored. And it's mind-boggling, not only that people are leaving this out of the equation, but when you bring it up to them, they want to fight. They want to tell you, oh, no, you got to keep your velocity up. And they come up with all these things. And then one of my favorite things they say, oh, you don't understand. And I think I do. It's a big math problem. And none of it's hard. But there are people who have been doing stuff for so long, a particular way, and I'm just going to be blunt and say it. They're doing it wrong. And it, again, brings me a lot of joy when we can measure this stuff, bring it out to people. And House just said the majority of systems don't get designed at all. It's absolutely true. And there's just so many things that can compound these bad designs. And the reality is, when it doesn't work right, people throw more capacity at it. And it's mind-boggling. But it also makes me giggle now, because I can confidently say, do the math, and the outcomes are predictable. So this is a fun topic. It's one of those things where we're really getting into the minutia of this stuff. If people just do it a little bit, I'm happy. But we can
And
talk
it's
about with what happens.
it's interesting that you mentioned you got to keep the velocity up, because we looked at some of the data here, Chris and I did, and the relationship between velocity and pressure drop and throw, and it's not what you think. I'm going to drop a tease. I'm just dropping a teaser. It's not what you think.
Yeah, and
Right.
I'm going to take Steve's comment right there about it's not what it thinks, and I won't be a spoiler either. But I was looking through some stuff earlier today, and I found some of the math that Steve had up on one of the whiteboards in the conference room from the last trip. And I've changed how I'm going to address things based off of that. And actually, it wasn't even from the last trip. It was from the previous trip before that. It was wintertime. And it was the kinetic energy equation and all that. And it's math. It doesn't lie to you. So it's how you get confident with stuff.
Except when it does.
All
I've been through that once before.
All right, guys, let's go to work. These people are waiting on some juicy content. Let's give it to them.
Yeah.
So if you're out there watching, we are launching this as an interactive webinar, and we've got this first slide put up for you to get the ball rolling. So this is just a test slide. So the question is, who's ready to play the game? So if you go to menti.com and you enter the code 1548114, you can log in and play this game through this webinar. There's a QR code right there you can scan and jump in easier. So either way. So I'm going to pause for a minute, and we're going to get this ball rolling and have people answer the questions. Once I see some movement on the screen, then I know I've got some people who are active and playing. Then we'll continue. So let's give it a minute. We'll let Ed talk some more.
What do you want me to talk about?
I don't know. Entertain us, Ed.
All right. When it comes to supply outlet coverings, for the longest time, and half the time I still have it now when I'm doing classes, I have this mental block. I can't call a register because it's a supply outlet covering. And it took me forever. And just recently I was going through some content, or it might have been during a class. Either way, it doesn't matter which one it was. I finally found where it says supply outlet covering, and it's on the friction rate worksheet. So that's why I've been calling it that for as long as I have, because, well, that's where it's housed. And that, and I kept calling, saying supply grills. And I don't want to say supply grill, because supply grill, it's not. It's a supply register. It's supply diffuser. One of those. I like to reserve the word grill for the returns, because I think that's what it should be.
We got somebody working. I'm doing it myself just to make sure we're working.
Yeah, I'm going to try and find it too.
Oh, I had to scroll down. Just so everybody knows who's watching, I had to scroll down on my phone to make it work. It was like it was showing it twice. So just FYI.
Yeah, you got like there's a window that pops up that looks like where you're supposed to be, and you got to close it.
Yeah.
Oh, we have to enter a code also, don't we?
Yeah.
15.
No, not if you scan the QR. You don't have to enter code.
For people. All right, I'm gonna give it one more minute just to everybody jump
got
in.
it.
The
Look at
code
me showing off.
Yeah, the code will stay up there for each slide. So just let everybody know. All right. Well, moving on. All right, so let's talk about what we wanted to answer, right? So I kind of threw some bullet points out there. Like when doing a friction rate worksheet, you know, the rule of thumb's like 0.03. That's the pressure drive everybody picks for a register. And what we're trying to vet out is that a good rule of thumb? And is it not a good rule of thumb? Ed, you want to add to that?
Do you want me to answer it, or do you want me to just give a brief opinion on it?
Why don't we do this? Between us three, let's do a thumbs up or a thumbs down if we think it's a good rule of thumb.
Well,
Ready?
before we do that, let me add this comment. The fact that somebody is actually going to even acknowledge that a register has a pressure drop and put it on a piece of paper to do some math, my nerd gland is just thumping nonstop. But to answer the question, yeah, I'm ready to do a thumbs up or a thumbs down.
All right, I'm ready.
Right.
You ready? I'm going in the middle. Yeah, I was thinking the same thing. I'm somewhere in the middle. All right, so let's ask a
I'm going to
question.
pull a house. It depends.
So the question to the audience is, do you look up your register and grill engineered data for your friction rate worksheet entry? Let's see what people think.
Now you're asking them directly. I'm going to be
Now,
incredibly disappointed if somebody writes no here. So there's peer pressure. Every participant should be putting yes right now.
yeah, they should, but let's.
I think this group would be.
It's anonymous, so we won't have your name. Try to vote with honesty. All right, I'm gonna give it just more minute. Let's see if there's comments, if anybody's having trouble.
Can you see how many people are connected?
Neil said it's 0.01 off, a big deal. I'll tell you, Neil, you'll have to wait to the rest of this webinar to find out. All right, moving on.
Oh, we're not going to address it now. We're going to do a whole bunch of questions, and then we're going to go back and address. Okay.
That's right. What do I do if my register does not have a listed engineering data? So that's the second big topic we wanted to address during all this testing. Could we kind of pick a grill and not have to worry so much about the engineering data? Could we find another way? And, so that's going to be answered. So second question, if an owner wanted me to use their registers with no engineering data, I would blank. Now, this is where you get to add in your own words. Let's keep it PG. No, let's see if that worked. Oh, there they come. They're coming in the corner. Not do it. 4 answers. Press enter to show the answers. Oh, there they go. Sorry, that was my fault. Not do it. Break out my duck blaster and test it. Tell them they own the outcome. See what they looked like before I answered. All right, we got some answers there. All right, let's go. The last thing we wanted to ask. How does pressure drop affect the throw of my airflow? All right, so last question before we get into the data. Do you take register throw into consideration during your HVAC design? Honest answers only. I don't think it matters. All right, here we go. All right, so that's a little fun before we get started. Let's jump in. Now, this is what we tested. So this is a stamp-faced grill. It's a 6x12 made by AirMate, which I think made by Hart and Cooley, and AirMate resells it. I don't know that. That's just my opinion. I think that's how the game's played. I didn't look it up. It's just what everybody told me, or Ed did. So
the catalog was the same.
They're close enough in design that if we tested both of them, they'd be within spitting distance of each other.
That's right. So I've highlighted what we've done. Now, this is just to give everybody watching kind of what we've done is we picked what we thought was the nominal flow that someone would probably send through this register. Now, not only one, we've tested 2 flows. So I thought the maximum I'd like to ever see come out of this grill is probably 200 CFM with that PI box below mounted to it. Now, we also tested this. We tested that at 200 CFM. We also tested it at 100 CFM. We did that so we could interpolate between the 2 numbers.
And Chris, I think you said you might sometimes put that on a 6 and have a lower flow, or on an 8-inch branch run and have 200.
Right. We had 2 PI boxes, a 6-inch top tap box and an 8-inch top tap box, both with 6x12 throw grills, because that's what's everywhere around me. I see it everywhere. If it's a bathroom, it's a 6x12. That's just how they do it here. And I wanted to see what's the good and the bad and the ugly of that. Now, my second grill is the higher end homes that I see around me. And I would say the lower states, this is very common. Some people upgrade to curved blade grills. Now, what's interesting about this curved blade grill is it does not have pressure drop on the engineering data, right? We've got CFM and we've got throw, but we've got no pressure drop. This is really interesting. So me and Steve talked about this for a while. You remember this conversation, Steve?
Oh, yeah.
So we're thinking that the reason this one doesn't have pressure drop is because it's adjustable. So if it's adjustable, how could you basically nail down the pressure drop? But I did some research and I found that Hart and Cooley's grill that's just like that does have a pressure drop.
Oh, okay. So that, and the interesting thing, as I think about it further, how you adjust those blades would probably affect the pressure drop, but also the throw, and they give us the throw. So yeah, it's a little weird.
Yeah. So these are the grills that pertain to me that I wanted to see. Now, moving forward, we've got floor registers that don't exist over here, right? And so these are for Steve and Ed, right? The ones they selected, if you guys want to talk about them, the floor diffusers. Oh.
Yeah, this is your standard floor diffuser that you see at the end of typically a 6-inch run. And we did 4x10 registers. They're pretty ubiquitous in Minnesota, at least, and I think in your neck of the woods too, Ed, right?
It's the most common size, and unless you're building houses for people that are 4 or 5 feet tall max, they're the wrong register. Manual T tells us we should get minimum 75%, if not a full hit the ceiling with the throw out of the register. And I'm not aware of many houses that are being built that have 4 or 6 foot ceilings. So it's a misapplication every time it's used. Now, it's the most popular. I've put tons of them in over the years. Super convenient to pop it out and sweep the kitchen floor right down in there. Lots of people have their kids hiding their toys in there, always filled with Cheerios and all that good stuff. But it's another one of those things. I'm not going to say you're going to have air conditioning air puddling on the floor, but you're not going to get the performance out of it that you can on the heating side, because if it's coming out of the floor, well, the heat's going to want to go to the ceiling naturally anyway. So it's one of those things. It's just the way it's always been, because it's just the way it's always been. And it's another one of those things that we do in our industry where we repeatedly make mistakes with choices because we don't pay attention. And I'm going to stop there because I think you have a better register to point out its performance that would fill the same hole. Correct, Chris?
No, we've only got 2. This one, and I think the one that's worse.
Right. Oh, okay. Because I would always go with the Hart and Cooley, not the Hart and Cooley, the Royal Air 531, which is that aluminum looking job. It looks like a lineal one, and they've got 9 or 11 feet of throw with the same numbers we saw on the previous slide. So.
Let me ask you this one, Ed. In fairness to all the people putting in floor registers in the Midwest and the Northeast, what do you think are the chances that regardless of what grill you put in there, that it's going to flow, that it's going to throw as far as you think it's going to throw, after they put a bookcase in front of it, or the couch is covering half of it, or even if they left, 6 inches between the couch and the wall for that thing to throw, it's not throwing 8 feet to the ceiling.
No, you're right. And that's it's a very fair comment. If you go upstairs in my dining room, our hutch sits right on top, and I had control over the whole situation, and that's still where I ended up putting it.
Yeah.
I'll brag about, we have a French door in the back, and typically people will put the supply outlet on the dead side of the door. Well, historically, we've always used a rug that goes the width of the door, and my wife is very adamant about you take your shoes off when you come in the house and they stay on that rug. Well, if I put it in the traditional spot there, then the rug would cover it. So I would have nothing in the kitchen and the dining room. But I did put it even further towards the corner, and it has the adjustable blades, and I can blow the majority of that air towards that window, which is the biggest source of the gain or loss in that area.
Yeah.
So it sounds like your guys' situation of floor registers is super mistreated, just like my area is with ceiling registers, right?
Well, I would say we're probably more mistreated because you could actually do a better job. There's not something in the way in the ceiling, but I think if you're using floor registers at all, you're probably not going to get the throw.
Yeah.
Unless people don't use furniture.
So this grill here is the last one we tested. It's the wood grill. Surprisingly, I could find no engineering data on it. Now, I do have this submittal page that
But
gives
it
me
sure looks pretty.
Yeah.
Yeah, that was good sarcasm, Chris, that you couldn't find the
Yeah.
performance data for it.
So it does have free area listed, which was something. So we captured that data. That may come into play. Let's find out. All right. So we need to talk about how we tested this so everybody understands that we did a good job, right? Here's what we did. We used the ASHRAE standard 120, which is the method for testing, terminations. What that looks like. Steve, do you want to walk us through it?
Yeah. So basically the standard explains that you have a long approach run of straight duct, and that goes to whatever your terminal device is, which in the ASHRAE standard includes both the grill and the boot. And basically it tells you how far away you should measure the pressure. And you can see, the big blue tape blob upstream of the boot on each one of those. That's at the prescribed distance that you're supposed to put your pressure probe away from the PI box or the boot. And then you measure how much pressure it drops between that location and atmosphere, because of course the other end of that terminal device is room pressure.
Right. So, and then the last picture just shows, make sure we sealed everything up from the register to the box, no leaks. So we took all the leaks out of play, just like it should be done in a house.
And in case anybody looked at all the blue tape and thinks that TEC is endorsing sealing ducts up with blue tape, we recommend blue tape to seal your ducts if you want them to stay tight for only an hour.
Yeah. All right, so let's get into some data. First, we got a question. So this is where we're going to ask the audience. The stamp-based register is blank, more pressure drop than the adjustable curved blade register at 100 CFM. Does everybody understand? So the answers are ×1, ×2, up to ×6. How many times more is a stamp-based register in pressure drop above the adjustable curve blade? ×6. Yeah, we're all over the place. ×2 to ×6. You know what? I need to put a count. I need something to do like a countdown timer over here. Oh, I got a little clock up there. I'll tell
Can
you
you
what.
see how many people are actually running the app right now, Chris?
No, I can't.
Okay.
But I'll tell you what.
You
I'll do it to the top of the 25-minute. We got a few more seconds. I'll just, every time I pop up a question, I'll just look at the timer. All right. So we got our guesses in. Looks like ×3 is the big win. So let's see. Times 5. So aggressively more pressure drop. But we need to pay attention to the amount of pressure we're talking about. So is it 5 times higher? Yes. That's a lot more pressure. But is it? We're at 0.001 on the curved blade and 0.007 almost on that blade. I mean, we're getting into a pressure that's really not noticeable on the friction rate worksheet. So it's higher, but it doesn't really matter that much.
Yeah, 5 times higher than what?
Yeah. Now that's at 100 CFM, mind you. So just that needs to be thrown out there. At 100 CFM, it's not that big of a deal. So the next question is, the same stamp face register is blank more pressure drop than the adjustable curved blade register at 200 CFM. So how many times more pressure do you think exists at 200 CFM? All right, we got 2 votes in for time 6. I know I got more people in here. I'm going to give it to the top of the minute. 20 more seconds. 10 seconds. Countdown. Get your votes in. All right. 4 times higher. That's the answer. But here's what we have to look at. Here, the pressure drop starts to get a little bit more noticeable, right? We're at just barely above 0.01. That stamp face register at 200 CFM is about 0.06. Now, if you're riding the fine line on a friction rate worksheet, that could put you in trouble a little bit, right? Ed, you want to say?
Oh, yeah.
You got something to say there.
No, I have unwritten rules on my friction rate worksheet. My happy place is between 0.2 and 0.25 for my available static pressure, and that can take me out of my happy place. But I'll back up and say if I had a pressure drop of 0.06 on a grill, that would take that grill right out of contention for me. You start to do everything with design is a circular process, and you got to trade things for other things. If it's a budget job and I only got $10 a covering and I got to go with a stamp face grill, that might lead me to need a bigger blower. And where do I want to spend my money? So there's always a compromise taking place, and 0.06 is a pressure drop that I don't want to design unless I'm absolutely forced into it.
So I think it's good to look at these in comparison to the number we might pick as a rule of thumb, which is 0.03.
Yeah.
So the stamp face is almost double that number, and the curved blade is half that number.
So we're going to get to that because this data is good, but we're going to get more into that friction rate worksheet in just a minute. But I'm just going to keep going. So this is just a side-by-side comparison slide, just so people wanted to see it between 200 CFM and 100 CFM to kind of see the noticeable difference in that pressure. All right, let's move on to you guys. The wooden floor register is blank more pressure drop than the steel floor register at 60 CFM. Now, this is what I took from Steve. Steve says this is about what's common in y'all's area, right? Seeing 60 CFM out of these.
Yeah, we're not putting 100 CFM through a 4x10 usually.
4. All right, I'm going to give it 20 more seconds.
I was like, House had to split for dinner and Tom's driving, so we might not get as many responses.
all over the place. All right, let's see. There we go, guys. The wooden grill is 3 times higher than the steel floor grill. Again, though, at 60 CFM, we're not in an aggressive, noticeable pressure that's going to affect us. I mean, the wooden grill at 60 CFM doesn't even get to our industry rule of thumb of 0.03. So I don't know. What would you guys think? Noticeable, not noticeable?
I'd say it depends on your airflow. If you got one you're really trying to push, 80 CFM through it, you probably want to stay away from that wood grill because it'll be much higher than the 0.02.
Yeah.
You might want to go with the steel one, but if you've got a bathroom that's got a 4x10 and you're only trying to put 40 CFM in there, it probably won't matter.
What's going to be interesting is seeing a throw. We're going to get to that. All right. So applying pressure drop to the friction rate worksheet. So what I like to say is like where it matters, right? So this is a snapshot of a friction rate worksheet that's been filled out. Now you'll notice I have on the supply outlet and the return grill outlet, I have 0.03. That's the industry standard, right? Rule of thumb. Now, when this is filled out all the way, I get a friction rate design of 0.08, which probably makes Ed's eye twitch.
Oh, no, I'm perfectly happy with 0.08.
Yeah. I know. It's like that whole thing. We have those conversations where you're like, don't say that because everybody locks that number in their brain.
Oh, okay. See, I'm still stuck on 0.1. 0.08 makes me smile. But the 0.08 and then the 0.05, yeah, I get what you mean there.
So we want to know the difference it makes when you don't use a rule of thumb. So we did that. So the next slide shows if we just change the supply outlet to the stamp face grill at 200 CFM, that would give us a 0.06. When we work that down, that's going to change our friction rate worksheet to 0.07, which probably not the biggest deal, right? I mean, that's probably not going to have you change duct sizes to achieve your goal.
Yeah,
There'll be a couple on the line that'll probably go up a size.
But that's only changing one, right? That's if we threw a bigger number in our return grill or change any of those other numbers, before you know it, we could be below 0.06 for our friction rate. And then we're looking at a bigger blower and things of that nature.
Well, I kind of threw that out there.
Oh, there you go.
So then I said, what happens if I do actually look up the return air grill and I come up with something similar, another 0.06? Well, that ends up giving me a friction rate design of 0.06, which literally puts me at the lowest part of the wedge, 0.06. So if anybody's wondering what that's all about, that's the friction rate chart. That's the wedge. Comes out of manual D. Ed, you want to expand on that?
Sure. The friction rate worksheet is the document that forces us to go collect all the relevant information. It's one of 4 worksheets that you fill out going through the full manual D process. And that chart that's over there to the right that has the 0.06 as the lowest friction rate and 0.18 is the largest, it literally lives at the bottom of that friction rate worksheet. And when you do the math, you can do your math that's above the friction chart right there, which is your friction rate is equal to your available static pressure times 100 divided by your total effective length. Or you can draw lines on that graph. And I usually recommend people draw lines on it because then you don't come up with numbers like 0.062 and then you find yourself trying to find that on the round up, round down, pick your favorite number. The wedge, as Chris was referring to, minimum 0.06, max 1.8. And if you exceed either of those numbers, there's guidance there. So if you don't have enough fan pressure and you have too long of a TEL, you could end up with a friction rate below 0.06. And then the guidance is going to be to increase the blower speed, change the I don't know what's behind there, or reduce the TEL. Oh, change the blower. Changing the fan speed, that might be a thing. Changing the blower is not a thing, because it's not you pull the blower out of the fan coil or the furnace. It's you're physically going to go up in blower size.
A new piece of equipment.
Yeah, you're picking a different piece of equipment.
Yeah.
On the other side of things, having very large friction rates, once you exceed an available static pressure of somewhere around 0.3, every time you go to size your duct, you're going to have to make the duct bigger, which is essentially reducing your friction rate. So I try and max my good grief, my friction rate. I try and max my friction rate at 0.1 or maybe 0.11, because as soon as you start to exceed those numbers, every time you land a duct size, you're going to exceed the max velocity, which the guidance in D is to make your duct larger to reduce your friction. Well, let's just start with a lower number for our friction rate. If you understood what I just said, great. If you didn't, I would highly recommend you find some more information on duct design.
Let's do a selfish plug here. If you like and you want to know what this is all about, ACA does have training. Ed is a trainer, and Ed will train you on how this is done properly if you go pay to see him in class.
And we take a lot more time to explain it than we did just then.
You're right.
So let me throw in a comment here. So Chris just did a great example showing what happens if you assume 0.03, and based on our survey at the beginning, most of you are doing that. But you end up with a stamp face grill that's actually more than that. So you're going to end up needing bigger ducts in, potentially needing bigger ducts on the edge cases. But I want to also think about what happens if, instead of assuming 0.03, if you're using those curved blade registers and those are more like 0.01, and then let's say on your return grill, let's say there you went with some egg crate grills that also have very low pressure drop. And so maybe instead of 0.03 and 0.03, you're going 0.01 and 0.01. Now your friction rate's going to go up. So maybe instead of 0.08, now you're looking at maybe 0.09, 0.1, which means that you're going to be able to have several branches that are probably going to go down a size.
Yeah.
So it's not a big difference if you're comparing 0.06 to 0.08, but really, if you're doing it correctly, you're probably comparing 0.01 to 0.06. And so now you probably are going to have quite a few branches that are going down a size if you're using the good grills, and up a size if you're using the bad grills. So
I just want to throw this out there just to kind of clear this up so everybody knows. This friction rate work chart right here that comes at the bottom, when you fill out your friction rate worksheet, you get down here. This number then goes over to here, and this is where you're going to size your ducts. That's what we're talking about right now, right? And at 0.06, between, let's just say a 0.1, you're going to have different duct sizes. Potentially, you're going to be deciding between a 6 and a 7 between these two numbers. So there is a possibility between engineering data and rule of thumb data, you could be swinging a duct size between a 6 and a 7 or a 7 and an 8. It's possible.
It's absolutely possible. But the one thing, and I think we're going to get to this in a little bit, but I'm going to throw it out there now. The whole manual D excuse me. The whole manual D process tells us that you can't have a duct that's too big. So if you do make these errors and you end up with a duct that's larger, the price you pay is for more materials. Or if it's in an aggressive environment, you might have more square foot of duct material in a hot attic. But as far as getting the proper flow out of the intentional holes in the duct system, there's no such thing as a duct being too big. So if you're going to error on the duct being too big, you never want the duct to be too small.
And make sure you put in balancing dampers regardless, but definitely if you upsize the ductwork, because that's the only way you're going to balance yourself out to get to victory.
Yeah, and if you're following the guidance in Manual D, the balancing dampers are a must. That's not a if you want to. That's a must.
All right, so we're going to get to the really interesting part. I didn't think this was going to be the super interesting data, but in my opinion, I think this data is more interesting than the pressure drop data, personally. So, quick snapshot here. This is the throw of the stamp face versus the curved blade register. So the stamp face, now this is at 100 CFM, right? The stamp face is moving about 3, almost 4 feet, and the curved blade's moving almost 5 feet. So not much difference in throw, and not very good throw at 100 CFM. What does that mean? That means you should probably pick a different grill and a PI box. You should go with something smaller if you're putting this in a 9-foot ceiling house, or any house for that matter, right? Unless you're living in a house with, like Ed said, 6-foot ceilings, this is the wrong selection. Do you guys agree?
Yes.
All
yeah.
right.
And well, this is not dependent on height, because with the ceiling grills, you're throwing across the ceiling, right? So to just clarify a little bit,
Yep.
you would only want to use these registers for 100 CFM if you're in a bathroom and you only need to throw it 4 feet.
Yeah. All right.
Not in the living room.
So here's the throw of the stamp face versus curved blade registers with 200 CFM. Now, this slide was super interesting to me because the curved blade grill, if you remember right, the pressure drop was very, very low, even at 200 CFM. But I got 8.5 foot of throw with a very low pressure drop. And I was going to think that I thought that more pressure was going to increase throw. I thought that's what we were going to see. And we did not see that. We seen the curved blade produce a lot of throw with low pressure drop. That's fascinating.
Yeah, that was exactly my intuition as well, is that when you get more pressure drop, it's because you're making the air go faster, right? Higher velocity, you would think more throw, but that's not what we're seeing here. It's that the stamp face grills is just chewing up the pressure drop, and it's not throwing the air farther.
Yep. So that's a big takeaway on that curved blade grill. So just as a comparison, another slide there, just comparing them. All right.
Yeah, go back one. So interesting to me that the stamp face grill is throwing almost the same, not a big difference at 200 versus 100 CFM. And the curved blade, there's a big difference between 100 and 200 CFM.
Mm-hmm. All right, where register throw matters. So this is the word question thing. Where is the proper place to point register throw? All right, I'm going to give it a minute. I think we got some late arrivers. If you're in here, just to let you know, there was or if you want to answer, you can go to menti.com and use that code, and you can add your answers into this presentation. All right, I'm going to give it just a few more seconds and we're moving on. Ed, I'm going to let you take the conversation on this next slide.
The one about where's the proper place to point the register throw?
That's right.
Well, that's easy. You put it so it doesn't blow air on people.
There you go. Have at it, Ed.
That's going to be first and foremost. Then you start getting into some, I don't know, almost oddball scenarios. There's going to be times where if I have control of everything, and let's say it's a clean slate and I have to put the ductwork in the attic because that's where it's going, I like doing short branch runs and coming a quarter of the way into the room and then picking a register that has enough throw to make it 3/4 of the way to the exterior wall. Register manufacturers, when they publish that throw information, they'll give you a number till the register hits terminal velocity. And every manufacturer, well, that's not true, every manufacturer. Some manufacturers will call terminal velocity 75 feet per minute. Some will call it 100. Some might call it 100 1/4. So I'm just going to say terminal velocity is 100 feet per minute on average. Essentially what they're saying is the air is going to run out of momentum at 7 feet. And that last little bit is going to carry us to the exterior wall, and then it's going to fall down the exterior wall. I, for a long time, designed my systems like that for all single stage systems. And I was very apprehensive about ever recommending it on systems that are going to run at half of their design airflow. But I've run into this, and I don't like using this as a metric for anything. And that metric is, well, I've never had anybody complain about it. Well, that's not the way you make decisions, right? You do it based off of math and testing and all that. But just recently, some guy I know, and he might be wearing a red plaid shirt right now, showed me some math. And he showed me that when the air is coming out of that turbination, when we're only running 30 or 40% of the system's design, there's a bunch of that cubed math involved. And the actual throw we're going to get out of that register is severely reduced as compared when it's running at the design or full CFM. So it matches perfectly with the not so precise. I've never had anybody complain about it because it explains it. You're not getting enough throw out of the register for somebody to complain that it's blowing on them. And I am not going to be nearly as concerned with getting the air towards the exterior wall if conditions are such that we only need to run at 30 or 40% of our capacity. So something that I didn't do in the past, I'm going to say, yeah, go ahead and follow that path. Whenever I can have less ductwork in the attic, I'm always going to choose that. The thing that was always on my mind was do perimeter outlets above the windows. And then if we're running at 30% or 40%, I know the air's getting out by the windows, but I know it's not that important when we're only at part load conditions. So it's all come full circle for me. I've never found anything in any of the ACA guidance that tells you to pick one or the other. So I think as time goes on, we're going to see it change to that is a good way to do it. So ultimately,
I'll add a little bit to that, Ed, and that is, like you said, when is the system running at 30 or 40% capacity? On a mild day, we're not doing a ton of heating, we're not doing a ton of cooling, and those aren't the days that people complain too much about being not being comfortable, right? Mm-hmm. It's when the walls and the windows get really hot or really cold that people get uncomfortable. That's where your throw starts to matter more. So as we move towards, so I don't know the answer to that. Yeah, is it going to throw a lot less? Yes, but is that going to be a problem? Well, maybe not.
I don't. I got to debate that.
What's that?
I got a debate here, and I just got to put this out there. I feel like when these inverter systems are ramping down, grill and register selection needs to be of the utmost importance, and you need to be hitting like a great deal of throw, because when it ramps down, you would still like to get the 4 or 5 foot of throw if your target throw was, say, 9 or 10 feet in the beginning.
The math tells us that's not going to happen, though. So that goes back to there's a solution, and you do the perimeter outlets.
So I guess we need to debate that a little. Like maybe that's our next
Well,
mid exercise.
so here's the other wild card. The other wild card is, I learned from Gary Nelson that if your envelope is great, it doesn't matter where you put them. You can do all sorts of things bad, and I think probably Neil Comparetto, knows this pretty well. They do a lot of low load homes, and it kind of doesn't matter. I think they still do a great job anyway. But when you get double, triple pane windows and high R value walls and good air tightness, it starts to not matter very much where you're putting the air, because it's gonna stay in the room. It's going to condition the room properly. When you start getting into leaky homes, single pane windows, not much insulation in walls and attics, now you're trying to really do a much better job with mixing and throw and all that stuff.
Yeah, Neil chimed in. I don't know if you guys saw it on your screen, but he said something to the effect of low load, low importance. And
Yep.
Few words and a good way to do it. Perimeter outlets, meaning exterior walls. Perimeter outlets could be the 10x4s under the windows, or the whatever shape you want to use above the windows, but in a proper selection. Every once in a while, I see a 8x8 3-way on an exterior wall above a window blowing back into the room, and I want to punch somebody in the face. So, I mean, that's just one of those things. I see round registers or square registers in the center of a room. In a commercial building, that makes perfect sense. In a residential home, I don't understand why somebody would want to blow the air towards the interior. Round registers, I think you guys have heard this before. What's the big benefit of a round register? You can't put it in crooked. Beyond that, there's really no advantage to it. So
that's a good one. Yeah. All right. I'm moving on. All right. So here's what we got. We got some takeaways from this class. I'm just going to throw this out there. So what have we learned? We learned that an adjustable curved blade register, or this one for that matter, at 200 CFM can nearly remove itself from the friction rate worksheet while giving the designer nearly a great deal of throw. For our example, we got about 9 feet. That's pretty good for a 0.00 something friction rate pressure drop. That's really good. So moving forward. Number 2, you should never select a register that does not have engineering data to back it up. There is net free area, but that is a less than ideal reason or use of a comparison to make a grill selection. Steve, I'll let you comment on that. Would you try?
Yeah, you shouldn't pick registers based on appearance. If you put these in the living room because you have hardwood floors in the living room, well, your living room's going to get less and your bedrooms are going to get more if the bedrooms have the stamped steel registers. So, if you want to choose your grills based on aesthetics, then you're not doing the proper air balancing. You're not going to get the results and the comfort that you're looking for.
That's it. And to take it a step further, registers get selected based off of aesthetics and cost 90-something% of the time, and performance, it's single digits. And it's sad.
All right, last takeaway. Using the 0.03 rule of thumb for register pressure drop could be too big or too small of a number. The proper decision is to look it up and confirm the pressure drop and the throw. And Ed was adamant that I add this statement. Same will apply for return air grill pressure drop.
Yeah. It's easy to put the wrong return grill in, and everybody that's in attendance tonight at one time or another have grabbed the kitchen chair and their Leatherman or some kind of pliers and went to straighten out the fins on the return grill because they make the spaceship noise. And everybody's, woo! Take it out and put a bar grill in. It looks better, right? A commercial bar grill, and it doesn't make noise. It's not really how you fix it. I mean, it could be how you fix it, but keep your velocities below 500 feet per minute on those stamped steel grills, and they'll always be nice and quiet.
There you go.
They won't hum. Do you guys know why return grills hum?
I don't.
Because they don't know the words.
That's the way he sees it.
And that's the way I see it.